Hi there, in this video we'll be looking into a problem called constructing a binary tree from preorder and inorder traversal. Let's jump into the problem statement. So given two integer arrays, preorder and inorder, where preorder is the preorder traversal of the binary tree and inorder array given to us is the inorder traversal of the same tree. We have to construct and return the actual binary tree. If you are not aware of the concepts of preorder and inorder, I suggest you to pause this video and go back and check what is preorder and inorder. It's a simple concept on how we traverse through the binary tree. So coming back, so what we are given with is two arrays. One is preorder, the other one is inorder traversal. We have to construct the binary tree using these two arrays given to us. Okay, so if you see this example, preorder here 3, 9, 20, 15, 7. Preorder, the root element comes first, then the left, then the right. Right here, it started with 3, then 9, then the entire right part. In the right part, the root node came first, then the left part, then the right part. Right, this is the preorder. In the inorder, root element comes in the middle. That's why 3 is in the middle. On the left hand side we have 9, on the right hand side we have the entire right subtree. In the right subtree, it is again inorder traversal, where the root is in the center, left child is in the left side, right child is on the right child. In inorder, the root lies in the center, right, and in the preorder the root lies in the first, then comes left, then comes the right. So if the array is given to us, let's say -1 and -1, that means it is just the root element, right? So output is -1. So the constraints given to us are like the length of the preorder is 3000 and inorder definitely, obviously, right? If there are n elements in preorder, we should have the same number of elements in inorder as well. And the elements can range from -3000 to 3000, and this solution is like the problem statement is for preorder and inorder arrays where it has only unique values. Okay, so each value of inorder also appears in preorder. That's the condition, obviously. Preorder is guaranteed to be preorder traversal of the tree. Inorder is guaranteed to be inorder traversal of the tree. So there are no bugs in the given two arrays to us. They are definitely preorder and inorder traversals of the binary tree. So what we have to return is a tree node which paths to the entire binary tree. So let's come up with the, I hope the problem statement makes sense to you. So let's come up with the solution. So we can take a similar example where we have 3 as the root node, 9 on the left side, and we have 20 here, and we have 7. This is not a binary search tree, it is just a binary tree. Binary search tree where the left element should be less than the root and the right element should be that is not that's a different thing. This is just a binary tree where each node has at most 2 elements, right? So if we start with preorder, the array will be 3, 9, 20, 7 and 15, right? Inorder array would be 9, 3, 7, 20, 15, right? So one thing we can definitely say is the first element in the preorder is always my root element, right? Preorder, it definitely has to start with the root, right? So this first element in the preorder will always be my root element, the first root element. So once we have the root element, then we move here to this subtree. This will become the root, right? So this we are sure this is the root element. The second thing which you can easily interpret is that the condition given to us is all are unique, right? We don't have duplicates. Once we find what is the position this element is in order, this 3 is present here, then we can say this is the left subtree, this is the right subtree, right? This is the left one, this is the right one, obviously, because in order on the left side we will have left subtree, on the right side we will have right subtree. Good. From this, you can easily interpret what is the length of left subtree, right? So what is the length of the subtree? The index of this one minus where we have started. So we will be recursively doing, right? So once we identify this, okay, we go to this part and this part, we apply the same intuition. So once we understand this is the length of left subtree, we can take this length and we can decide what is the left subtree in this part. It would be this one. This would be left part. This would be right part. Right? Now we can apply the same concept of identifying the root for this subtree, left subtree, identifying the root for this right subtree. So here in this case it has only one element, so 9 would be the root. In this case 20 is the the root of right subtree. Now we take this one and we go and check here and we identify what is the left part of this, what is the right part of this, right? One thing which comes to your mind is we have to know, based on this element, we have to identify where it is present, right? Where the index of this element is present, right? So for that we'll have a hash map which holds key value. The key holds the keys 9, 3, 7, 20, 15, and the values holds the index 0, 1, 2, 3, 4, right? 0, 1, 2, 3, 4. Why we need it? So once we, from the pre-order array, we identify what is the root element, first root element. We have to take this and search in the inorder to find the index of it. We can easily find with the hash map. Again, we have every time we cannot traverse this in order to find where 3 is present, right? We can, if you maintain a hash map, we can directly get the index and we can say that left side is the left one, right side is the right subtree. Now taking this, I will go to this one again and I will find the left and right from this one, and I will say, okay, this is the first root of this subtree. Okay, it's a recursive call. The first step is we take the root, okay, from pre-order. The second step is find index of root in order, right? The third step is we have to find what is the left subtree size, right? We find what is the left subtree size, and we, from taking that, we take the subarray from this with the size we got from here, right? We will get left and right subtrees accordingly from pre-order and inorder. Both are required, because we have to send this part for a recursive call where this left part get resolved. We send the right part where the right part gets resolved. Right, the same process, right? So let's code this. So the first step is, as I mentioned, we'll have a map of integer, integer. Let's call this as map only. We can call it as inorder map. So hash map, right? Hash map. Now I have to iterate through my I less than my inorder dot length, right? I plus. Okay, so map dot put, have to put inorder, have to put the element first, inorder I comma I. Inorder I comma I. Once this is done, I'll have my recursive method built get node, okay, get node, where I am starting with my pre-order, okay, and my pre-order would be 0 and my pre-order initial length would be pre-order dot length. We will take the index length minus 1, whatever is the index of it, right? So then we go to the inorder and we do the same 0 comma inorder dot length minus 1, and one more we have to pass is the map, right? Let's create this method. Okay, let me, don't worry about this. Okay, so this is pre-order. I mark it as p start, pre-order start, and p end, okay, and this is my int, this is also an int, then int I start and I end, and my map, right? Map of integer comma integer map. So in this method, so let's first get the root element. So root element would be the first element of my pre-order, right? So my pre-order start, then the index of root index in my map. So get root, that is fine. So then I have to find left size. What is my left size? So for left size, what I have to do, from the root index I have to minus my I start, right? So left size, to get the left size, I got that. So if I minus I start in order, what is the starting point of the in order, I'll get my left index. Now let me construct the tree node. So equal to new tree node, I'm passing the root element. Let me return it before I forget. Now I have to construct my left side and the right side, right? So node dot left is equal to node dot right is equal to, so I have to call the same thing with just few manipulations. So here the left side, okay, what would be the new p start, right? What would be for the left hand side? It would be my, I know the left size, right? So I have to pass in the pre-order of it would be p start plus 1. That will be the starting point of my left part, right? What is the end of it? The end of it would be p start plus my left size, right? In order I have passed as is, and the what would be the left side, left part in the in order, I have to minus. So the end would be p left's root index minus 1, right? In order, this would be I start itself, right? To root index is in the in order, what is the root index? Minus 1 we are doing to get the what is the left subtree start and end index in the in order array, right? So next, the same thing here, when we move to the right side, this would be root index plus 1, right? Root index plus 1, and this would be root index, right? We are looking for the this is not plus 1, this is not plus 1, this is, we are looking for the right in the pre-order. So we got the, in the pre-order would be p start plus left size plus 1, right? This would be p end. In order, it will end at definitely I end, right? And where is it starting? In the in order, we are looking for right in the in order. That would be my root index plus 1, right? What is the breakout condition? Breakout condition is simple. When my p start becomes greater than p end, that's when I have to break out, right? Let's run this. Okay, the test cases are accepted. Let's submit this. Okay, the solution got accepted. Yep, I hope the solution makes sense to you. Thanks for watching. Let's meet in another video.